Welcome back. In this video, I will derive the Wicking equation for the inclined capillary. The goal of the derivation is to use the Wicking distance that we have previously derived when we're talking about wicking in an inclined capillary, and then use the Hagen-Pozzoli equation for the inclined capillary by plugging in the delta P, which is equal to delta P capillary minus the gravitational effect, using the setup on the right where alpha is the inclined angle. The small x is the moving distance, and the big X we call the equilibrium rise Wicking distance. And this h, big H, will be called the equilibrium rise height. What we want to do is to integrate the Hagen-Pozzoli equation and then verify the Wicking equation can be derived as follows, where we have t explicitly and we have x implicitly. We can start by realizing the pressure difference can be written in terms of the Wicking distance big X. So let us copy down the Hagen-Pozzoli equation and then derive from there. And in the inside, we have 2 sigma cosine r divided by x. But this form is very similar to the Wicking distance, which also has a 2 sigma cosine theta. So that if we want an x in there, then we'll need to have 2 sigma cosine theta divided by rx. We already have r in the big X, but we need rho g sine alpha. So we multiply by rho g sine alpha at the top and bottom minus rho g sine alpha. So that the whole thing here and plus the r here can be written as the big X. Then we have rho g sine alpha at the top. And here we can group the rho g sine alpha together so that it comes out the outside. We have big X divided by small x minus 1. After having this form, we can then further simplify this equation, rho g sine alpha, so that we have a common denominator, small x, and at the top we have big X minus small x, so that x and x cancel to 1. Right, the next step would be to integrate. So we want to separate the variables. So on the dx side, we'll have dx, that's right, dx on the right side and dt on the left side. Dt will only have dt, so it multiplies to the right, but I write it in the left. And for dx, I write it in the right, so that we'll invert everything here. 8 mu r squared rho g sine alpha inverse and big X minus x, small x at the top, dx. You want to integrate everything. We'll realize that this whole term is a constant. It can be taken out. And the integral of dt is just d. We take out the constants. We want to integrate x, big X minus x. We can get the integral from Wolfram alpha or do it by hand. Wolfram alpha gives me that this integral equals to negative big X, natural log of big X minus small x minus x. And we can simplify this out by taking the big X out. We have big X minus natural log of big X minus small x divided by big X, so that they cancel out to x. Remember that this is an indefinite integral, so there is a plus c constant. And to evaluate this constant, we need an initial condition. And in this case, when t equals to 0, it has not begun wicking. So the wicking distance, x, is also 0. So when t of 0 equals to 0, small x is 0. So if this is 0, all the constant goes to the left is also 0. The x is also 0. This small x is 0, so we have negative natural log of big X. Minus x, which is 0 divided by thing, is also 0 plus c. So we have c equals to natural log of big X. And we substitute that in. Remember, we have everything on the left. We have negative natural log of big X minus x divided by big X plus c, which is the natural log of big X. And remember the natural log property. If we have something minus something, then we have a division within the natural log. So we have division of big X divided by big X minus x divided by x. And this can again be written as, if we invert the inside of the natural log by taking the negative of natural log, so it flips, and at the bottom we have x, and at the top we have x divided by x. We will have 1 minus big X at the bottom, small x at the minus small x at the top, big X at the bottom. Now we have derived the Washburn equation for the inclined capillary, where T equals 8 mu r squared 1 over rho g sine alpha multiplied by big X at the top, multiplied by negative natural log of 1 minus the ratio minus the ratio. And this is the equation that we're looking for. Now we have the Washburn equation for an inclined capillary. Then we can see that at some approximation at the small ratio x divided by x, we'll have recovered the Washburn equation for horizontal capillary. And when this ratio is small, it means that the whole thing is far from equilibrium. So if it's big X divided by big X, it's big. When it's small, then it is far from equilibrium. For example, the whole thing is X, and small x is just a tiny bit of that, so it is far from equilibrium. I use the Taylor series approximation to show that. So we first copy down the constants. And inside it, we'll have natural log of this thing. So the small x here will be the ratio. Let's write out the first few terms. For n equals to 1, we have negative 1 to the 1. And x, which is the ratio, the first power divided by 1, plus minus 1 to the second order, and the ratio to the second order divided by 2, and plus, let's say, everything that is order to the x, the ratio third. And lastly, we have minus the ratio equation. Then outside the constant stays the same, but inside we have minus minus is a plus, and this whole term is just 1, 1. We'll have x divided by x. And then minus 1 to the second is also a plus. 1/2 the ratio squared, plus everything to the third order, minus the ratio. And the ratio cancels out, so we'll have everything 1/2 x divided by big X squared plus order Now we have simplified the equation using the Taylor series approximation. When x divided by big X is small, the order of the ratio to the third goes to 0, and the whole term cancels out. So we can write it as all the constants sine alpha, oh, and then the inside we have 1/2, so the 8 goes to 4. And then we have small x at the top squared divided by big X squared, but this one x cancels out. We have this thing goes to 1 and leaving a big X at the bottom. Note that big X is the equilibrium Wicking distance that we have seen earlier. So we can plug this in, have 4 velocity rho gr squared sine alpha x squared divided by, so everything is inverted, so 2 sigma cosine theta rho gr. The rho g cancels out, r leaving only one r at the bottom, and 4 cancels out to a 2 at the top. Mu survives, sine alpha is cancelled out, x squared survives, and then we have sigma cosine theta bottom. Now we can solve to the Washburn format, so the x is at the left and t is on the right. So we have x squared equal to t is at the left, so that t multiplied by r theta cosine theta times sigma divided by 2 mu. And to take the square root of both sides, we have, which if we rearrange, we have r sigma cosine theta divided by 2 mu t, everything square root. This is exactly the Washburn equation. So we have verified that at small ratio, we can recover the Washburn equation of a horizontal capillary using the Washburn equation for an inclined capillary, meaning that at small ratio, gravitational effect is negligible. Because Washburn equation for inclined plane, not inclined capillary, is reduced to Washburn equation for a horizontal capillary. So the gravitational effect is negligible. In this video, we have derived the Washburn equation for an inclined surface, and we can see at the approximation of small ratio that is far from equilibrium, we can neglect the gravitational effect and just use the Washburn equation for the horizontal capillary.